So these are all the properties of the materials, that magnetic properties of the material. So now we are going to see the classification of magnetic materials. So how we are going to classify the magnetic materials? The magnetic materials are generally classified into three types based on the behaviors in magnetizing the field. So the three types are diamagnetic, paramagnetic and ferromagnetic materials, which are dealt in this section. So now we are going to see that materials, how we can classify that materials and what is the property of the materials. Okay. Now you see that materials are classified into three types. One is the diamagnetic material, next one is the paramagnetic material and ferromagnetic material. So first we are going to see the diamagnetic material. So diamagnetic material, how the diamagnetic materials are classified. Okay, so see that when the diamagnetic material is placed near to the magnet, it moves from the stronger part to the weaker part. So when the diamagnetic materials are placed in a magnetic material, it moves from the stronger part to the stronger magnetic field to the weaker magnetic field. So this type of materials are called diamagnetic materials. So it can move from stronger part to the weaker part. That type of materials are called diamagnetic materials. Why that materials are moved in the stronger part to the weaker part? You know that the cause of diamagnetism. Why it is that atoms are revolves around the nucleus. So that electrons also revolves around the nucleus. It has the magnetic moment. So the magnetic moment is perpendicular to the rotation of the electron. Okay, this is a magnetic moment. Magnetic moment means product of the flow of current into that area. So it is always perpendicular to the rotation of that electron. The vector sum of magnetic moment of that atom is 0. Okay, so the electrons are moving in a random motion in the atom. When that atom is placed in a external magnetic field. So when the magnetic moment is parallel to the magnetic field, so what happened? It will slow down the moment of the electron. So the magnetic moment is decreases when it is parallel to the applied magnetic field. Suppose that applied magnetic field is opposite direction to the magnetic moment of the electron. So the magnetic moment of the electron is increases. So when it is opposite direction to the magnetic moment. Okay, that initially that electrons are in the random direction. So the resultant magnetic moment is 0, but it is placed in a magnetic moment. They are arranged in a particular direction, different direction. Okay, so it is placed in a uniform magnetic field. It is not in a particular direction. They are arranged in a different direction. This type of materials are called diamagnetic material. Bismuth, copper, lead, silicon, nitrogen at standard pressure. So these are all the example for the diamagnetic material. Okay, so the diamagnetic material placed in the uniform magnetic field, the anti-parallel means it increases. The susceptibility, see that psi chi is that is greater than minus value but less than that 0. That permittivity is positive and greater than 0. Susceptibility is negative but permittivity is slightly less than that unity. The superconductors, the diamagnetic materials are superconductors. The superconductors are perfect diamagnetic materials. The expressions of magnetic flux from a superconductor is the transition of superconducting state. That's called Meissner effect. See, the superconductors are floating. So it is called superconducting. This property is called superconductor. This conductor is called superconductor. When superconductors, when placed in it is in the normal state, so that electron field is passing through it, but in a superconducting state it is excluded the electric field. So it's called Meissner effect. So Meissner effect means superconductor behaves like a perfect diamagnetic material below transition temperature of Tc. So it is used in the trains, magnetic levitated trains, superconductors. So the trains are levitated from the trains, so it is moving without any friction. So it is used in the trains. Second thing is paramagnetic materials. In paramagnetic materials, each atoms and molecules net magnetic dipole moment and a vector sum of orbital spin magnetic moments are due to magnetic option. Here, so that paramagnetic materials are placed in a strong magnetic field. It moves from the weak magnetic field to the strong magnetic field. That type of materials are called paramagnetic material. So, the material which is placed weak magnetic field, it is moving towards the strong magnetic field. That type of materials are called paramagnetic materials. Initially, before applying that any external field, that electrons are in a different direction. They are not in a regular direction, they are in a random direction. So, the vector sum of magnetic moment is 0. So, when my external field is applied to the paramagnetic material, that magnetic moment is 0 because they are in a different direction. When the external field is applied, non-uniform magnetic field is applied, that electrons are arranged in a particular direction. Not it is completely arranged in a particular direction, slightly it is deviated in a different direction, but they are arranged in a particular direction. So it has the quickly can convert the ordinary substance to a magnet. So it has the properties higher. So example for the paramagnetic materials are aluminum, sodium, calcium, platinum, chromium. These are all the example for the paramagnetic material. And Chi, susceptibility is greater than 0. That is means susceptibility is positive, permeability is greater than unity. So susceptibility is positive, permeability is greater than 1. So it attracts the paramagnetic material and it is inversely proportional to the temperature. So it is inversely proportional to the temperature. That means temperature increases, the paramagnetic materials decreases. That can be explained by Curie's law. So here the Curie's law, when temperature increases, so the current I is directly proportional to 1 by T. So here it is a flow of current and temperature is inversely proportional to each other. First one, diamagnetic material is independent of the temperature, but here paramagnetic material is depending on the temperature. When the temperature increases, thermal vibration will upset the alignment of the magnetic dipole moment. Therefore, magnetic susceptibility decreases. So I is equal to directly proportional to B0, that is applied magnetic induction. Or combining that two equation, you can write I equal to B0 by T, where B0 is the applied magnetic field. Here C is the proportionality constant, or that is called Curie constant. So the IC is called Curie constant. It is called Curie constant, or B equal to mu naught into H. So that is the relation between the magnetic induction and that magnetization H. H is a magnetization, B is the magnetic induction. So it's a relation between the magnetic field and the magnetization. B naught equal to mu naught into H, or we can write chi equal to I by H. Chi equal to I by H. So combining these two equations, you can substitute in the equation 3. So equation 4 and 5, substitute in equation 3, you will get chi equal to C into mu naught by H. So it's called Curie's law. So it's called Curie's law. When you draw graph, you will get that is decreases when temperature, the chi is decreases when temperature is increases. Okay. So it's called paramagnetism. So initially the diamagnet is independent of the temperature, but paramagnetic materials are depending on the temperature, and it is inversely proportional to the temperature. That is explained by the Curie's law. So Curie's law is between the susceptibility versus temperature. Susceptibility and the temperature. This is Curie's law explain that. Okay. Next one, we are going to see the third properties of the material, ferromagnetic material. So here it is in a saturation magnetization. So that's why it is there arranged in a applied magnetic direction. That is paramagnetic material. Next one is the ferromagnetic material. In that ferromagnetic material, that molecules from ferromagnetic metal possess a net magnetic dipole moment in a paramagnetic material. So now we are placing the material which is stronger part. See that it's a material. It is ferromagnetic material placed in a magnetic field. It moved from the, see that it's moved from the weaker magnetic field to the stronger magnetic field. So here para and ferro, the both materials are moving from weaker material field to weak magnetic material to strong magnetic material. So this is called the ferromagnetic material because initially that atoms are arranged like this. Before applying that any external field, they are in a random direction, but here all the electrons are arranged in a regular direction before applying that any external field. See that we can classify into ferromagnetic materials. We can divide into small domains. The domain contains the different number of electrons. They are in a different direction. So the net current is 0. So net magnetization of this is 0. For each domain it contains 10 to the power of 11 atoms per domain. So it differs for the different domain. It is not a constant value. So different domains are having the different direction before applying that any external field. Net magnetization is negligible because 0, because it is in a different direction. Now it is placed in a uniform magnetic field. So what happened? They are arranged in a direction of applied magnetic field. They are arranged in a direction of applied magnetic field. So it's called ferromagnetic material. Right? See how it is arranged. After removing that magnetic field also, it remains in the same direction. So hard ferromagnetic material, because it retains its magnetic material. So these things are made up of, it is used to make of permanent magnetic material, alnico, steel, trigonal. These are all the materials which is used to make the permanent magnetic materials. Okay. So after removing the magnetic field also, it is remain in the same direction. Slightly in the removed direction. So soft, suppose the direction of the electron is changes, means that is called soft ferromagnetic material. Does not changes means that is strong ferromagnetic material. Soft magnetic materials are iron, cobalt and nickel. These are the soft ferromagnetic material. That means when you remove the external field, it will change the direction. So chi, the susceptibility is positive and large. Relative permeability is large. So the susceptibility and permeability is very large. Okay, so it is strongly attracted to the ferromagnetic material when it is placed in a magnetic material. Here the Curie-Weiss law is there. The Curie-Weiss law, in that Curie temperature, when temperature increases, the ferromagnetism is decreases due to the increases thermal agitation. So we are increasing the temperature. See here the magnet is there and nickel paper clip is there. It is connected to that ion. According to that law, as temperature increases, the ferromagnetic decreases due to the increased thermal agitation of the atomic dipoles. At a particular temperature, ferromagnetic material becomes paramagnetic material. This temperature is known as Curie temperature. See, when your temperature is increases, it will break. So in that particular temperature, it changes from ferromagnetic material to paramagnetic material. It is not attracted with that magnet. See that metal is fall down. So initially it is stick with the magnet, but temperature increases, it changes to from ferromagnetic material to paramagnetic material. So this is the experiment explained in that Curie temperature. So in which temperature it changes from ferromagnetic material to paramagnetic material, that temperature is called Curie temperature. So this relation, so now we are going to relate the temperature and the susceptibility, that is called the Curie-Weiss law. These are all the materials which is used for Curie temperature, some ferromagnetic materials.